discuss the complex number system. So I found this little chart that kind of summarizes the sets of numbers that we have. So we've seen a symbol U and we've seen upside down U. Who would like to remind the class which one's the and which one's the or? Volunteers? Oh. Somebody tried to unmute themselves?
The or is on top.
The or is on top? Yeah, so this is the and, this is the or. This kind of looks like, do you see the and has an and here that could be thought of an upside down U. So that's how I remember it. So this is an and, this is an or. Now this is sideways. So basically it's like contained in. So these natural numbers are contained in the integer numbers, and integer numbers are part of or contained in rational numbers. So rational is Q, or quotients. And then those are contained in so on. So I have here more information than you usually would have seen. We call the numbers beyond rational ones, we call them irrational, but there's actually two ways to describe them. There could be called transcendental, the ones that are using pi and e, but also we can call them algebraic. Algebraic because you can do algebra on a number like square root of a number, and you have decimals that go on forever without repeating pattern. So those irrational numbers can be broken down into like different parts that you can call them. What we're going to be studying right now is the imaginary numbers. Both could be algebraic or transcendental, right? Because it could have the pi on it. So this little I is what I'm going to teach you today. What is it? But also we could say that we could take this part and add it with any of the real numbers. So if you have real numbers and imaginary numbers added together, we call it complex numbers. All of these in purple is complex numbers. Some of them could be called transcendental complex numbers because it has pi in it, or it could be called algebraic complex numbers because it does have just the regular roots on it. So I'm going to teach you about these imaginary numbers right now. And there's a blurb here about infinitely many. So the integers, rational numbers, and algebraic numbers are countably infinite, meaning there's different types of infinity. At university, when I took pure math courses, we talked about, you know, that one infinity and another infinity, they're not actually the same things because some infinities are bigger than other infinities, which is a little weird concept, but that's how it is. So it says countably infinite because you can actually start counting them, meaning that there is a one-to-one correspondence with the counting numbers themselves. Counting numbers are the natural numbers. Real numbers and complex numbers are uncountably infinite. Like we can't even count them. So I kind of mentioned that before, that when we were doing, was it topic 1 lesson on the very bottom? Yes, I kind of mentioned this before. I said over here, I'll zoom in. I said that the ones that I could kind of pinpoint were rational numbers, right? But I said in between every single one of them, we have many, many, infinitely many irrational numbers, but also between each one of those, we also have rational. So it's very hard to pinpoint irrational numbers because they're just all over the place and you can't really call them countable. Anyways, that's not part of the lesson. Let's get to what is an imaginary number I. So imaginary number I will allow us to deal with questions like square root of a negative. Before we would just say no solution and stop. Well, there is actually a way to discuss solutions that just allow us to have more other types of numbers, namely imaginary numbers to work with. So the definition for I will be when we have square root of a -1. In other words, sometimes you can see actually that when you have I squared, it's equal to -1. Both of these statements are identical to each other. So if you have a complex number, I kind of mentioned it. So if you have imaginary part added with a real part, then we call it a complex number, not just an imaginary number. And then we also have conjugates. So conjugates could be recorded as a little star on it or a bar. So conjugates you've seen before. For example, if I said 2 plus root 3, the conjugate version would be what? Someone unmute?
2 minus root 3?
2 minus root 3, right? So same thing happens with a conjugate imaginary number. It would be a minus bi. So if it was plus in the middle, then you change it to a minus. If it was minus, then you change it to a plus. And then finally, I'm going to just quickly show you that all of these could be drawn on a plane. So when we're drawing real numbers on an x-y axis, then we had both of them as real numbers on both axes. Here we're going to have real numbers here. And here we're going to have imaginary numbers. Now for imaginary numbers, they don't call them capital I here. I will. Okay, so real goes on x-axis and I for imaginary on y-axis. So here's what it's going to look like. We'll have 1, 2, like usual, 3, -1, -2, -3. But on the top here, you'll have 1i or just I, then 2i, then 3i. On the bottom, -1i, -2i, and so on. So when you're trying to sketch a particular complex number, if I wanted to sketch, let's say, let's call the imaginary number z1, if I had just 2i, that's going to be plotted just over here by itself. If I had, let me change the color so I can go over with a little legend. Can I change color? You know, color to red. Here we go. And let's do a blue one. So Z2, if I had, let's say, -3 minus I, what would that look like? Well, you go -3 on the x-axis and -1 on the y over here. This is the point Z2. Okay. I think that's it for definitions. Let's see how do we work with them. So it's going to be very similar to your concept check. So let's start with the first one. If you have a negative under the root, here's what you're going to do. You're going to split up that negative under the root as -1 separate from the remainder of the actual number. And then, of course, with 98, you can think about what numbers divide into 98 that are perfect squares. Can I ask Alex to unmute yourself? You'll be the first one I start talking to. Alex, do you think of 98? Does it simplify a little bit in terms of perfect square numbers?
Yeah. Divided by 4, for example.
Yes, you can divide by 4. Or you get decimals actually dividing by 4. Is there something else? Maybe it doesn't divide evenly. Let's say
7,
2,
sorry.
2 and 49. Oh, 49 is a perfect square. So I'll write it out like this for you. Now, 49 can change into something. What, Alex? Square root of 49 is? Issues with the mic, probably. 7. So this one becomes a 7. I'll put it side by side with the 3. The square root of -1 is going to be I, and then root 2. So this is equivalent to 21 I root 2. I prefer to put the square root at the end. Of course, you could put 21 root 2 and then an I, but you have to really be specific that root 2 is not captured. So the root is not on the I at all. Yeah, Alex, your mic was acting up, was crackling, and then I couldn't hear you. So that's okay. I don't know. You probably could troubleshoot that a little bit later. Let's go on to David. David, can you unmute yourself? We'll do the next one together. So when you have powers on the I, there is a way to simplify that. And let me just show you something before that, though. Hang on, David. You can say hello in the meantime.
Hello.
Okay. So we're going to be using the fact that I squared is -1. Come on, give me a place for me to move that. Okay, we're going to be using this concept that I squared is equal to -1. But we don't have squares here, we have other powers. So the best way to do this, David, is to rewrite this in such a way so that we have a multiple of 2, so multiple of 2, and then multiplied by the remainder, whatever the exponent here will be the remainder. So can you tell me how we can change that 345 to be a multiple of 2 and the remainder version? So the remainder could be 1, right? So what would be the number over here so that when we add the two numbers together, we get the original exponent? 300 what?
344.
344. Beautiful. We're going to do the same thing with the other one. So we had +2. So I, and I know there's negative on it, so your choice, you could say this is equivalent to negative.
Negative 22.
Yeah, you could do negative 22 with a -1, or you could just say negative 24 with a +1. Do you agree? I'll go with this version because I want a +1 here, so it's easier to see like terms. So why would that be useful? The reason why that is useful is because we can actually definitely say that this is I squared to some sort of power. So because it's even exponent, what do we multiply 2 by to get 344? What would be this exponent?
172.
Nice. 172, and then the I beside that. Same thing here, we'll have I squared with a new exponent. What would be that new exponent?
Negative 12.
Negative 12, and then we have the I. So why is this useful? Well, because we know that I squared is -1, we can just replace this with -1 with 172 I plus 2, -1 with exponent -12, and I after that. Are you okay with that so far, David?
Yeah.
Now, -1 to the power of an even number, would that be +1 or would it be -1?
Positive.
Yeah, so we have +1 I plus 2. Now this negative exponent just means that it has to go on the bottom, like so. But regardless, if it's on the bottom, is this thing going to be +1 or -1 overall?
Positive, so it would just be 2i.
Yeah, so we'll have just 1i plus 2i. And what is 1i plus 2i in the end?
3i.
3i. So we got something that looked very complicated to be just a single complex number, or imaginary number, because it doesn't have a real part. But this is it for that question. Any questions, David, or anybody else?
No.
All right, Sebastian, can you say hello?
Hello, is my mic fixed?
Yes, it works. All right, so Sebastian, if you had a question like this, and you had a stretch on one of the complex numbers minus a stretch of another, basically we want to clean it up by distribution. So imaginary numbers really work like your usual number. So what would you say after you distribute here, Sebastian?
So it would be 6 minus 2i, and then plus 10 minus 15i.
Do you see any more like terms that we can combine?
Yeah, so you can do, let me just, so negative 17i plus 4.
Plus 16.
Oh, plus 6, yeah, sorry, I thought it was a
It's
negative
okay.
somewhere.
So let's do one more because that was very easy. So same thing with adding and subtracting. You could also have multiplication. When you're multiplying, you're going to do the FOIL like you would usually do, and then just one extra step after that. Okay, so go ahead. Tell me when you expand 2
Okay,
times, or sorry, 2
so
times
2
7.
times 7 is 14, and 2 times, so that's plus 4i,
Yes.
and then minus 35i minus 10i. Oh, wait, 10i squared.
10i squared. So this is the place where it's slightly different. You're not going to leave this I squared as it is. You're going to replace it with -1.
So it's positive
So,
10?
yes, so in the end, it will be 24 minus 31i. Did I do that okay?
Looks fine, yeah.
10 here, 10 positive plus 14 is 24, and then 35 and 4, 1 is negative, so negative 31i. Is this okay?
Seems good, yeah.
All right, so thank you, Sebastian. Jasmine, unmute yourself. Say hello.
Hello.
Okay, so for division, Jasmine, we want to multiply by the conjugate. It is improper to leave I in denominator. Very similar to when we were doing it with square roots and we had to rationalize the denominator. Same thing happens here. So quick reminder, Jasmine, before we even start this, if I had 3 over root 5 and I wanted to rationalize that, it was just a monomial, so we just multiply root 5 on top, root 5 on the bottom. If it was a binomial on the bottom, so let's say it was 2 plus root 5, then what we had to do was to multiply by the conjugate. So we multiply 2 minus root 5 on the top and 2 minus root 5 on the bottom, and then we would FOIL, etc. Remember how we kind of did that before?
Yeah.
So here, if it was just I by itself, then you would multiply by I and I. So if it was 3 over I, then you would multiply by times I here, and that's it. But if it is a binomial like this question is, we're going to multiply by the conjugate. So, Jasmine, what is the conjugate for this 2 minus I?
Is it 2 plus I?
Very good. So 2 plus I, both top and bottom, so we're not changing the question. And then we're going to just do distribution. So on the top, you will get what?
You'll get 12 plus 6i.
And on the bottom, what are we going to get?
You would get 4 plus 2i, and then negative 2i, and then negative I squared.
Nice. Okay, so the I squared is just a -1. And these two things cancel off completely because 2i minus 2i. So we have 12 plus 6i on top of what number? Just one number. What would that number be?
Negative 4? Wait,
Try
no,
again.
just 4. Yeah.
4, subtract a
Oh,
-1.
Okay. So if it's 4, subtract -1, it would be 5.
5, beautiful. Okay, so either leave it like that, or of course you can record it as the real part plus the imaginary part separately. So all of these have to look like the format that you have a real part plus the imaginary part. All of the questions that we've been doing so far ended up being that way. Take a look. Real part, imaginary part, real part, imaginary part. Here's imaginary part, but technically there's a real part of 0 there, right? And then same thing here. Okay, so I think only one question left. And Jasmine, you can mute yourself. This particular one, I'll just do myself and people can ask me questions. So absolute value, what does it mean for absolute value? So I'd like you to kind of tie this together to vectors. So let's go back to this little picture. And let's look at the red dot first. So if I asked you, what is the magnitude of 2i. You're basically asking yourself, what is the distance from 0? Remember how we talked about the absolute value could be thought of distances to 0? Well, from 2, even though it has an I, the size of that is just 2. So you'd say that the distance from 0 here is just 2. Let's do the blue one. The blue one is going to be, what is the distance from this point to 0? Well, I need to draw that line to know what that is. And that creates a little triangle here, size 3 on the top and size 1 on the side here. And we're looking to find the length of this diagonal on this right angle triangle. What would we use to find this? On the right triangle, if we know 2 sides, how do we find the third side?
Pythagorean theorem.
Pythagorean theorem, which will be square root of 3 squared plus 1 squared, which is 9 plus 1. So the square root of 10 is the answer for this question. So if I asked you magnitude of a complex number, is basically like magnitude of the vector, right? So in vectors, we did that. We said that the vector is the one that's pointing from the origin towards the point. And so if this was point A and this point B, then we said that this would be AB vector and then magnitude symbol on top of it. Very similar concepts here. So back to our question. Oops. This is my last question. So in this situation, I need to visually maybe show you. We're going to have root 17 maybe somewhere over here and negative root 8 maybe over here with an I. So this is the dot. We're looking to find the length of this line from the origin. In order to do that, I need to see my triangle. So my triangle would be size root 8 here and size root 17 here. And so the magnitude of that would be square root of root 8 with a square plus root 17 with a square, which is just 8 plus 17. What's 8 plus 17? 25, which is in the end just 5. So magnitude of this particular one, it just ends up being just a 5. Any questions how to do operations with complex numbers? All right, so I'm going to send you to your teams as well. You have a choice. You can, of course, do this particular set of questions. It's not going to take you too long, so might as well get it over with. If you get stuck, you can look at Danielle's little video link here. Feel free to use it. Or you could say, I'll leave that for tonight, or sorry, tomorrow night, and just work on the review for functions, and you can work together as you're creating your cheat sheets or practice test or whatever you need to do. Any questions about that? I'll stop the recording.